Okay, now let's look at some of them in one by one, and we'll see how each one of them behave. Okay, so basically, we are looking at buildings with these characteristics. We are looking at buildings with an average floor height of about 3.2 meters, roughly 3 to 3.2 meters, depending upon what are you using for floors. Then this allows for 2.5 meter clear ceiling height within the space, including all of the stuff inside there. 6 meter additional height is included for lobby space. Normally, first floors are always 2-floor height. So that's a big problem for frames because frame is most weak at the base. And if you also increase the height, it becomes really weak. So frames are very weak at the first starting floor where we start, where they have the maximum drift problem. For buildings 60-story and taller, 6.4 meter tall, intermediate space, somewhere between another high floor is provided for storing of the mechanical systems and lobbies, and some more architects are using this a lot now. Swimming pools, gardens, landscaping, they put in the middle of the building. And that creates this problem with the soft story and many things we will talk about later. And then, so now, these are the primary systems that we can discuss, but of course, we will go beyond that. Internal systems, like I said, systems which are placed inside the building are moment frames, bearing walls, frames for walls, coupled walls, frames, walls, outriggers, and belts. We will talk about them as one group. Second group is external systems, which are placed outside the building, not in the middle. Those are tubular systems, wall plus mega columns and outriggers and belts, diagrades and mega frames, and plus more. So these are the two broad categories of structural systems, one that are placed inside the building and one that are placed outside on the exterior part of the building. And then all possible combinations. So bearing wall systems, you can have light frames with shear panels, load-bearing shear walls, fully braced systems. This is the internal systems. Shear walls, only diagonal bracing systems, then special moment resisting frame, ordinary moment resisting frame, dual systems with shear walls and frames, and so on and so forth. So these are then subcategories of internal systems on how we connect things, and we will talk about most of them today. This table is quite old, but still useful. People try to give a rough range of the structural systems in terms of the number of stories. And you can say flat slab and column is the lowest one, flat slab and shear walls. They put it here, but now flat slab and shear wall has gone up to 60-story because we add other things on top of that. Alone, flat slab and shear will not work, but then we add something more, we will see. Flat slab shear walls and columns, coupled shear walls, rigid frame, widely spaced perimeter tube, and so on and so forth. Shear wall frame, shear wall, haunched girder frame. This is an old list, but I still include it because you will find it in many books, many references still there. But many of these limits are no longer valid because people have been evolving these systems to make them more efficient. And there are many variations of each one of them. So roughly gives you these 14 systems all the way up to 110 floors. Interior system, I showed you this diagram already. So we have braced frame, this one, all the way up to the buttressed core. You can look at it. We already saw this. So this is categorization done by this guy in 2018. This is a little bit more recent based on his survey. And these are the external systems, steel braced tubes, bundled tubes. So please look at them for completeness of the discussion. This is the second time I'm displaying them, and especially these, these super frames and mega frames and so many things. So most of them are being used in some building or the other. Okay. And as you can see, that there's every very tall building comes up with a new system almost every time. But more interesting now, practically, is this list, which is a big problem now. This is the list from the ASC guidelines, minimum design loads and associated criteria for buildings and other structures. And this list is very different from what you saw earlier. This is the one that the designers are supposed to deal with because this is the code. And this list is very long. It used to be 5 or 4 systems. in 25, 30 years ago. Now it has 30, 40 systems listed in there because every person is developing a new system and it has to go back to the code and they have to put some formulas on that. So this system is, these pages on system, you should get hold of this reference. I will be giving you several references later. So, but you can see here, just the bearing wall system, it has 21 subgrouping. Can you imagine? It used to be one system, bearing wall, 20 years ago when we started practice. No worries. Now within that, you have 21. Then building frame system, you have another 17, 20 subcategories. So now the problem is this. Why this is like this? Because everyone created a new variation of the thing. And then codes, because codes have to give limits or numbers for design purposes for each system. So every time a person develops a new system, they ask the question, what factor should I use? These are the numbers that you need for the design. I'm not going to talk about them now. We will come back to them when we do the design criteria. For example, you need response vector, response modification factor, overstrength factor, CDR factor, seismic category, and so many things, and height limits. So each structure has a height limit. No limit and NP, not permitted. So this is a very restrictive table. If you follow this table, you can't do anything actually, because it tells you mostly what you cannot do. Very few you can actually do. So if you're looking for a very tall building, you will not even find it on certain systems because there is not permitted in high seismic category. So if you are designing a building in a high seismic category, you will find that most of these systems are NP, not permitted. So that you come up with the question, what do I do then? Right? So that's why this performance-based design is coming up and new systems are coming up. This is just 2 pages. This is 7, 8 pages of this list that you can see from there, right? So first of all, you have to find your system in between this one, which is very hard because each description is very not clear. Is your system, for example, this says bearing wall system, ordinary reinforced AAC masonry shear wall. What does it mean? Then it says light frame, cold form steel wall system using flat strip bracing. What is that, right? So there are many sub-definitions inside, and most of them not suitable for tall buildings. Anyway, because these codes, they are developed for buildings which most commonly used. Tall buildings have separate, different guidelines, which I will share with you later. But I just want to make sure that you understand that the basic design codes like ASC may not cover the kind of structure that you want to design. This is no limit and not permitted. Then we have all these, so many factors over there. And 5, 7, 6 some categories, seismic category definition, and then combined with the system definition, it becomes, and then the analysis type definition, it will become very complicated. So which means that you have to see what system are you doing, where is it located, what software do you have, and what kind of analysis you can do. The codes will tell you all of that. That for this earthquake zone, for this structural system, you need to do this type of analysis, and you cannot do this type of analysis, right? So there's a lot of rules to follow when you start doing your project, and you probably should understand them, most of them. Now let's come to first system in the list. Most starting base system, moment frame, which I also, this one that I showed you earlier. So moment frame is basically a frame beam and a frame column, and inside could be a frame column or a gravity column. Or, so this is the distinction between a gravity frame and gravity column is whether it is going to be part of the load resisting system or not, right? Now, why in this one I put inside column and inside beam as gravity only? Because we are trying to move the load resisting system to the outer boundary of the building as much as possible, following one of the rules. So inside column is not going to be so useful. If you remember, it has to be as far from the center as possible. So if the column here is not going to help you much for lateral loads, right? For a tall building especially. So that's why, but in some cases we use the entire frame. Okay. So normally the perimeter frames are lateral load resisting frames generally, and interior frames may or may not be part of that, depending upon building height and other things, right? So you can have the option to use the entire frame on each bay, or you can only have the outer frames used for that. Okay, so that's the basic concept. And then the frame will look something like this. I've already shown you. So this is a moment frame. The beams will control the efficiency of the moment frame, not columns. So you have to have as deep beams as possible, which will be quite difficult to do. So the efficiency is quite low by themselves. So you will have bending moment diagrams, bending moment everywhere. In every beam and column will have bending moment. We have a shear force. You have an axial force. You can see from here now the important thing. Axial force is only on the outer. That means they are really the one which are providing that couple for resisting things. One interior, they're not really efficient in axial force. So one of the rule was it must be an axial, which means interior columns are not helping you much. That's why we can make them as gravity also, right? Okay, so that's the basic idea of that. Then deformed shape, you already saw that we have the deformed shape like this, so it becomes straight, deforms a lot here. Then support reaction, these are the primary support reaction, very small. This is only 6, this is 26 from the lateral load. So outside columns are carrying most of the lateral load, as we expect. So you need to put the gravity loads on there to balance that. Otherwise, you will have a lot of tension on this column. So that's the basics of the frame. Frame is very good for low rise, large, but not so good for tall and narrow buildings. So concrete frame, people say you can go up to 20 stories. Yes, but very hard to actually manage even 20 stories. You will have to need to use small spans and deep beams. And you can also use steel. So in US especially, they use steel column and steel frame, and then the connection between the columns and frames becomes very critical. Steel moment connection is much harder than concrete moment connection. Because concrete, when you cast together with the typical reinforcement, mostly gives you a rigid connection. Steel, you have to make a rigid connection, and a lot of detailing is needed to make that effective. So steel frame is normally less than concrete frame height. Rigid frame can go higher. These are large diameter, large columns and large beams. Then we come to the wall systems. Now we can have a frame and we can put a wall either inside or anywhere on the system. This is not necessarily for elevators. Currently, we're talking about structural system. We would come back to the core again. So you can put a shear wall core, or you can put a wall anywhere. So let's look at that. So this is a simple study on effectiveness of placing the same wall segment on different parts of the building. So if this is a frame and you want to put walls in this one, 4 walls, you can put it in multiple ways and you can see the efficiency. So for example, if you put these 4 walls here, one here, one here, one here, like that, 2 on each side to brace this side and this side, you will see that the displacement has come down from 21 to 11 millimeter. Both direction displacement is nearly equal, and this is fine. So half the displacement has been reduced by almost 50% by adding those 4 small walls into the building, right? So that means they really help a lot, increase the stiffness by twice. If you move them inside, similar, didn't change much. So that means as long as they are symmetrical and they are placed in the same amount of each direction, their stiffness, effectiveness is similar. But if you put them as a core, look at that, almost 3 times now, the stiffness, effectiveness has increased much more than putting the same walls in various locations. And that's why the core, as I mentioned to you, moving the walls to the core helps a lot. because now they are no longer walls helping the frame. They are four walls helping each other also to create a strong core. So its behavior is now very different. And that's exactly why core-based structural systems are more efficient internally than distributed wall systems that you can do. And that's why core, as I mentioned to you earlier, is very important for a tall building, as long as we can utilize it and we can find a place to put the core. So your core should be your first place to start if walls and frame is your solution alone. Okay, and then when you move outside, if you only put them in one direction, you are in serious trouble, because in one direction you reduce, but other direction, nothing, no effect. So that's a mistake that many engineers make. They just put the walls in one direction, forget to put in the direction. You get unsymmetrical response and very weak structure. And we are going to talk about dynamics later. And this is one thing that we are not going to let it happen. The two-directional dynamic properties will be very different in this case. So that means this is a no-no system to follow, that you just put the walls all four in the same direction. All four like this one also doesn't help. So which means that the walls must be in both directions, number one. Number two, if they are core wall, they are far more effective than distributing them outside. Okay, so that's what we learned, combining walls and frames together. All right. Okay, so we typically, you can add those and you can go up to 50 stories like this one. You can put the big core. Normally the cores are getting big, they're quite big, not just only that. So that means the core is quite effective, and we can use that. There is another variation of the wall and frame system, which is called building frame, which says that, okay, I will not use my frame at all for lateral loads. I will use only the core wall, for taking 100% of my loads. And if I do that, then that means that I just can use flat plate for just gravity load. So that means the frame or the columns and the floor only carry gravity load, do not assist the shear walls, have no coupling effect, and walls alone as cantilevers carry the entire lateral load. So that's another option. And that is a very good option. Why? Because then you don't need to detail so many joints for ductility and confinement and reinforcement and everything, and you don't need to make the beams very big. Because if you make the frame has to be moment resisting. If moment resisting, has to have ductility. If it has to have ductility, you need a lot of detailing and reinforcement to do that. But if you decide that, okay, my beams are not part of the system, the slab is not participating, fine, I don't need to do anything. Just let the wall handle everything, right? So that's the building frame concept, and especially useful in steel structure, where they just make the steel frame without moment connections and let the core wall take care of the lateral load, or the bracings take care of the lateral loads. So that's the advantage of using this kind of system. So basically, everything is gravity frame, gravity column everywhere, and just the core is there. Okay, so this is a variation of that. So you have the same, looks the same, but detailing is different, design is different. Okay? There are many rules about how you design this one. But the height range is less, 35 only, 30, 20. With frame, it can go up to 50, 60 floors. Remember that, because you're not assisting it. There's no coupling effect. Okay, but we can increase this later. We will find that there is a way to break this limit. We'll come back to that in a few minutes. Right now, we're talking about basic systems. Okay, I want to start this topic, a very important one, which brings us back to 1 + 1 greater than 2. And there are three parts to this equation. And this is the basis for many systems that we will discuss now in detail. And the discussion starts from two very different things: frame and shear wall, dual and coupled systems. So we are going to talk about how we put them together and make it one system, and how we connect two of them and make a third system. Coupled system, it means that frame and shear wall are working together and they're sharing the load by a certain percentage. Typically, they assume that wall should take about 75% of lateral load, frame should take about 25% of the lateral load. That's the definition of a dual system. Whether they carry that much or not is a very different question. The second is that we couple them. When we couple them, then they become a new system, a third system. Then the sharing is not predetermined. Then they are one system, which means they are coupled, and they are not shear wall and frame dual system. They are a coupled system. And coupling happens in two ways, and we will see. One is because the two systems behave differently when we connect them together. There is a interaction between them. And second one is that they change the way the load is transferred. The first is that they join together and they share the load, and then one is deformation, another deformation, they try to balance, and then they have interaction between them. The second one is they are coupled. That means the load transfer mechanism is not changed. And then coupling has two parts to it. There's a coupling with the traditional way, and then there's an outrigger effect, which is also a coupling, but in a different scale. So we are going to discuss now these three things together, step by step. So this is the first issue, that we have story sway. We have a frame that goes like this one. Each story has a kind of a mechanism. So each story has what we call a drift as a shear. So there's a net shear effect of the story, which is one story moving this way, another story moving this way, and then displacement divided by height will be the one, and that's the total displacement. We already talked about these two factors. This is a frame behavior that we typically see. Then there is a wall behavior. That means we bend the wall as a cantilever. So it starts from here like this one, and then at the top becomes like this. So if you notice the previous one, it remains straight at the top. It doesn't bend like this one. It just shears. That means it just moves on the sideways, but it doesn't deform like this. So that's a shear mode. It's interesting that the frames actually deform in the shear mode, and walls actually deform in the bending mode like a cantilever. So they will deflect like a big cantilever. So the top will no longer be straight. It will become like this, and then it will be zero, and then it's bending. And so this is just a frame description of the same thing, that if we have very rigid system, it should deform like a wall. So there's a wall bending, which deforms like a cantilever, and there is a shear deformation, which is the frame, which is the horizontal movement of each floor because the load is applied, and then there's a horizontal. So these are the two modes of deformation in two systems. So when we put them together, then this is what will happen. So they will start to interact with each other. This is called the traditional shear wall frame interaction, where shear wall wants to go this way and frame wants to go this way. So when they are put together, at some point they are pulling each other, at some point they're pushing each other. So in the beginning, the frame is trying to go this way, wall doesn't want to go. So the wall is pulling the frame backwards. At the top, wall wants to deform as a cantilever, frame is trying to be straight, so it pulls the wall together. So this shear wall frame interaction helps both of them. It reduces the wall deflection at the top, and it reduces the frame deflection at the base, because wall has zero displacement close to the base. And so the frame, as we saw last time, the frame tries to deform a lot. First story shear is lot, and this wall pulls it back. So this interaction works very well, and this interaction was recognized long time ago, and a lot of people wrote a lot of paper, and it depends on how the two are connected, what kind of connections do they have. So this is the dual effect of the frame and shear wall. Next effect is a different one, which is the coupling effect, which is this way. That means when you deform two things together, I showed you the 1+1 thing. So when they deform, this coupling, these beams tend to bring them back together. they don't allow them to deform independently. So one wall is going like this, one wall is going like this, but the top, because they're connected, so the top cannot be two steps. They try to be straight. So these coupling try to bring them back through a shear force induced in this one, which converts into axial forces in the two elements. So pure bending in the two walls now converts into axial forces, one tension, one compression. So basically this section extends. Rather than having one wall here and one wall here, like these two, luckily we have now these two, rather than these two walls like this, they become one section that with the connection. So the moment of inertia, as you can see, is a cube of that. So the stiffness certainly multiplies. Not exactly, there's a shear lag between them, which is called this one. This is a shear lag. So this becomes coupling now. So now you have tension, compression, and shear. From single bending of two bending moments, we have axial forces generated, and this axial forces will depend on the coupling effect, and these coupling beams will be subjected to shear, a lot of shear, and bending moment at the same time. So now this coupling effect is not the same as shear wall frame interaction, because that was just because of the shear mode and the bending mode becoming together, and that will produce forces in the floor, which is connecting them. But this is going to produce shear and bending moment in the elements that connect those two, whether it's two walls or whether it's a wall and a frame, will have the same effect, right? So that coupling effect is the key where we use to increase the stiffness by a large number, not just adding them together. Now, which means that these couplers or coupling beams or couplings will become the critical part of our system. So if they fail, then the coupling effect is lost. And the problem is that their bending moment, when you connect them together, depends on their size. So if you make them deep, they will attract, because short length, they will attract a lot of shear and a lot of bending moment. And if the capacity is not enough, then you try to increase them. When you increase them, they attract more force. In fact, there is no way sometimes to increase the size enough for capacity until you actually make it solid and no room is left between them, because every time you increase the size, the stiffness becomes large and they attract more force, and you have to design bigger, and then you end up with an impossible situation where the coupling beams cannot be increased in size because of the headroom for the passing. So that means that this yielding or this tracking is inevitable in a coupling beam, is inevitable. You have to allow it, and you make use of that so this becomes the nonlinear connection between the two parts, like a fuse. So they will be in a certain situation. These cracking will happen, yielding will happen. We have to allow it, we have to manage it. And this becomes one of the key challenge in the design of the tall buildings, how to design these coupling beams to be very effective, at the same time, not so much that they cannot be designed, right? So this balance between them is going to be the key for a performance of a tall building. And you will find, as we do go later, that design of the coupling beam is one of the most difficult part in the design of the tall buildings. And it's unique to tall buildings. Okay, so we'll come back to this one. So this coupling effect is one, interaction is two, and third one is outrigger effect, and we'll come back to that later. Let's first concentrate on this coupling effect of this one and move forward. So let's study the coupling effect. So this is a wall, this is a frame, and I put a coupling here. This is a very small coupling, just flat slab, no beam, nothing. We're just a slab, there is no coupling. Here we put a beam which is the same beam, so there's some coupling here. And here I put a very deep beam between them to increase the coupling effect. So we will see when we increase this coupling elements, what changes in the response. So this is the key moving forward. So when you do that, you will see that now the deformation this deformation is here, this is here, and this is much less. So clearly the deformation of the building reduces because of the coupling effect, right? Not because of the shear wall frame interaction, because that was already connected, even with this slab, because there's horizontal connection that was already present. That should have worked. But this is an additional effect because of the size of the connection between them, which is creating a coupling effect. Okay. And then if you go forward, you will see now this one here. So that's the bending moment produced between them. So here, almost very small bending moment. This is more bending moment. This is very large bending moment. So you can see that the bending moment now in the coupling beam is increasing as the size of the coupling beam is increasing, which means that if you, and the effect of the coupling is increasing, when you size increase, the displacement is controlled, drift is controlled. But the negative thing is that the bending moment in that element keeps increasing, even though the bending moment in the main beams doesn't change much. But the coupling area bending moment changes significantly by change in size. And then the axial loads here. So you can see here that axial load now in this column was very small. Because of the coupling effect, a lot of axial load goes to this one. So now we have been able to convert the bending in the wall into axial load in the column because of the coupling, because of the shear between the wall and this one. So bending moment, so the way it happens is that it deflects and produces bending moment. That bending moment in return produces shear, bending moment divided by the length in that beam. And that as the moment increases, the shear increases because it's just bending moment divided by length. So that gets you large shear, and that shear adds up into the columns and becomes a large axial force. So that mechanism is what is happening here, that you can see here, and then the axial force becomes very large here, which is a good thing, and that is the shear. So you can see a small shear here, large shear, and very large shear here. And this is the problem, because when the shear will become large, you have to design the coupling beam for that much shear. And very soon you will run out of the shear capacity of that coupling beam. So the shear capacity is now controlled by the size of the coupling beam and the concrete strength and the limits by the ACI. So invariably, even if you are able to provide a lot of reinforcement for bending moment, you will never ever be able to provide enough capacity in shear. So the coupling beams first consequence is they will start to fail in shear if you let this happen. So which means that now you cannot utilize the coupling beam's advantage, because the shear capacity will almost always be smaller than the shear they will attract because of the length, because shear is coming from stiffness, and stiffness is related to the length of the coupling beam. The shorter the coupling beam, the higher the shear will be, because moment will be large. So which means that this shear is now going to be a problem. And what do we do now? Okay, let's see. How do we handle this problem? We have talked about this so much in the last semester. We had the capacity-based design lecture. We have a test. We have a task project which does exactly that. It allows the beam to yield for a certain capacity, and the shear, as I told you, I gave you the answer already. This shear is generated because of the bending moment produced, and which means control the bending moment produced, right? That means limit the reinforcement in the coupling beam to the max, to calculate it backwards from the shear capacity. So the shear will never exceed the capacity of the beam. You control it by controlling the bending capacity. That's the principle of the capacity-based design. We tested that in the lab. That's the way to go. So remember, increasing things is not the answer. You should not do that, because there's a limit to increasing things. So you will always run into a problem. How much can you increase? The code will not allow that. So increasing things has a limit. So you cannot think about increasing. That's not a good way to solve problems. Okay. So the solution to the problem is very, very simple. That means, and I showed you cracking and everything. I gave you so many openings, but nobody picked it up. So the solution is that you provide, whatever capacity of the shear you have, you first of all, utilize maximum capacity, provide maximum reinforcement, provide diagonal reinforcement. Whatever you want to do that, but there's a limit to that. Get that shear capacity with the maximum that you can, steel plate, whatever. They're all not the problems, they're not the solution. And then from there, calculate how much moment is needed to produce this shear and limit your flexural reinforcement to that level. So you will never have a shear failure because moment will yield first, and yielding of moment is not a problem because that's perfectly fine. Ductility, we studied about ductility so much. We have ductility of 8. So no problem with ductility. You let it yield. That's why the ductility is there, to let that yield and not be damaged. So that's the first application of all the theory that we talked about, strut-and-tie model, capacity-based design, nonlinearity, ductility, everything is here. One thing. Understand now? So next time, please think outside the traditional way of thinking. So that's the way to do this one. Okay. Now you can see also that the column reaction will change. The next column goes from 7 to 36 to 53 axial load. So that means the foundation and everything will change. So as soon as you put the coupling, the whole distribution of axial forces changes. And this is back to our concept. Strategy number 1, convert bending moment into axial forces. So the coupling helps to do that. It converts the bending moment into axial load, which is much more efficient that way. And it also helps us to put the fuses. So this is the concept of putting fuse. You know, when you have expensive equipment, you put a fuse behind on the main. So if there's an over supply of electricity, the fuse will go out and your equipment will be saved. This is exactly the case here. You put a fuse in bending moment to protect your precious shear failure because that is brittle. So you never let the failure happen in shear by putting a fuse for bending moment, which is easy and which is not going to, and so that's the idea. And then the coupling beams have, replaceable coupling beams, so many things have come up later. Okay, anyway. So same thing we can do with coupled walls. That one was coupling between a frame and a wall, previous example. This was between frame and a wall. We can do the same thing. We can take 2 walls, and this is the key. Take 2 walls here, this simple slab connection, beam connection, deeper and deeper, right? You put deeper beams to connect them, coupling beam couplers between walls, not between wall and frame. And you have the same advantage as I showed you earlier. You get this one, and then you get this one. Look at the deflection drift control. So much drift has been controlled. Here, drift is like this much. Here, the drift is only 1/3 or 1/4 or even less than that, 1/5, 1/6 of that, right? So you have increased the stiffness by 7-8 times by simply using those coupling effect, right? And these coupling are the same. And these are the most easy coupling to do, most useful because normally they are the elevators or the doors between walls, and above the whole region, we use it as a coupler. Right? So that's the second coupling that is very, very common and very, very useful, coupling between 2 walls and coupling between frame and wall. Okay? So that coupling effect is the key for improved lateral performance for tall buildings, because wall alone, and then here you can see very shear, and here I use shell element, so you could not do directly bending moment, but if you cut a section cut, you will see it will be very large, right? Because I use shear shell elements to model that beam to be geometrically more realistic. And then you can see here you can see now tension, compression. These 2 walls are bending independently as 2 separate walls. So each one of them is pure bending moment. So tension, compression. Therefore, here gradually, and here you see tension and compression, they have shifted to the extreme edges. Because of the shear transfer between them, they start to act as one big element. So this is a wall with opening. This is one wall with opening. This is wall with larger opening and so on. So I showed you that also. So coupling effect, once again, can be used in a very effective manner by connecting 2 walls by appropriate system, and same rules for coupling apply as coupling between frame and wall. Okay. So that's how the shear will look at the shear increasing over there, and then forces and then everything. And same thing, you can put a coupler between these two walls and a frame, so the whole thing goes on and on. You can have coupling between walls and wall, and coupling between wall and frame. You can extend it, you can spread it around, depending upon the system you have. So the same thing goes here. The force is increased, and you look at how the tension compression moved outside completely because of that coupling things. So coupled shear wall systems, and that same story. Now, this is a completely uncoupled system. We talked about shear wall and flat slab, right? So flat slab, when you use flat slab, unfortunately, you cannot couple anything because flat slab do not have beams. And if they do not have beams, you don't have couplers. So if you do not have coupling between them, then they are two separate walls. That means you have to now design the system purely wall based on wall deformation. So there's a limit how tall you can go on this one, because walls as cantilevers cannot go too far unless they're coupled. You cannot find this limit. It depends on the size of the wall and many things. So it's a cantilever. So typically one wall, you cannot have more than 1/12 ratio, length, height over width, 12. So which is not good, because this, if the story is, let's say, if it's 100 meter, you need 10 meter, 12 meter walls to do that, right? So that's not always possible. And still bending will be very large, because cantilever walls will be still bending a lot. You've seen it. Individual walls will never work. Well, they will work until 20, 30 stories, but beyond that, they will not work. They will stop being effective. This is the situation with that. So zero coupling to some coupling. So the coupled systems are very good up to a certain height, up to a certain 30, 40 stories. You can have 20 story, 25 story, you can have walls without this one, and beyond that, after 40 stories, you will start to get into trouble. True tall building problems start to come after 40 stories. Up to 40 stories, most of the traditional things can make it work. So you have this problem here, and then like this one after. Okay, so walls can be like this. Wall can be distributed like that. Columns can be distributed like that. These are some of the way the wall shapes and things. So these are typically a building, a real building, where the walls can be U-shaped, columns with the wall, L-shaped, single wall, column. This is the way that the system is normally typically distributed. Now the trick will be to utilize all these things effectively, connect them together as much as you can, finding where the best connection will help us. Okay? Because architects will want something like that. They will not really. So you have to start with what is available and try to figure out what I can connect, where I cannot connect, what kind of effect I will utilize. Start with frame-shear wall interaction to frame wall coupling to wall coupling, right? These three things you already know now. So also the arrangement, we talked about that, you have to distribute the walls very well. We will talk about this again when we do the dynamics and the modal analysis. We will discuss a lot about this one, not today. Just give you an idea. These are some real examples of tall buildings that use systems. So this is using a very large core wall system. There's a basement here, there's a podium here, there's a core wall, very strong core wall. So flat slab will be fine here, for example, because it's not too high and the wall is really big. And it's a core wall, which is probably also coupled within the system. So it's not a problem. Another bearing wall, this is the bearing wall system. Every partition wall is a shear wall. So you can have flat slab again, because no need for a coupling. And the building is not that tall. It's 30 story only, 30 story only. So, but you can see every room is divided by shear walls. And this direction also, it's a partition walls, no partition walls, only structural walls, which is excellent. Construction-wise, cost-wise, speed-wise, fantastic. And in Bangkok, Bruksa company, they have built a precast system. All the walls elements are precast, all the slabs are precast, so very easy to make. And they just have a single core which is holding everything together. And these walls, precast walls, are post-tension, so they are acting very nicely together. AIT solution, or we help to design that system. Coupled shear walls here, as you can see here. So we have the coupling between them. Okay, now we come to the problem when that will not work. What do we do when we go beyond that? What is the next solution?